Okay, so it's Thursday, and I got some good progress today. My delay lines came in, and that's what you see here is the prototype of the phase comparator. And let me just talk about what I intend to do, and I'll describe what the LEDs are showing. So basically, what I want to do is I want to find out where the edges of the 10 megahertz clock are in relationship to the PPS signal, so I can get a better idea of how far off my frequency is without having to wait for the full count time, because every time you want to do that, if you have to wait for an edge to slip, it could be minutes. But if I can look at where the edges actually are in a finer grained way, then I can adjust it sooner. So basically what I have here is I have the delay line, and it's this Dallas part, and they don't make these anymore, but on eBay they had some supposedly new old stock out of China, and they're from 1988, and one of them didn't work at first, and I found one that did. I'm glad that one of them worked. But basically there's an input, and then there are 10 taps, and each tap has a delay of either plus or minus 2 nanoseconds or plus or minus 5%, whichever is greater. And this part, nominally, it's 10 nanoseconds per tap. So what I want to do is I want to have the clock come in, then I get a delayed version of the clock that goes, that version of the clock then goes to a set of latches that is latched every time a PPS comes along, so I can freeze the position of the clock pulse. And right now I'm showing it with LEDs, but in the real system, or after I'm done with this, I'll have a I2CIO expander, which is like this guy, that I can use to have the processor read it. So the first thing I did is I actually measured what the delays are. So the first tap delay is 14 nanoseconds, which is actually, I said, is 10 nanoseconds per tap, but the first tap, it's a nominal 16 nanoseconds. And then the next one was 27, 39, 52. And so there's generally 12 to 13 nanoseconds between each tap, which means that here tap 10, it's actually 126 nanosecond delay, which means that since my clock edges are 100 nanoseconds apart, this last tap, when I see an edge there, it's actually the next edge, or sorry, it's the previous edge, and so it's been wrapped around. And so if you look at this, really the first tap, since it's a 14 nanosecond delay, and the eighth tap is a 1 nanosecond delay, then between tap 8 and tap 1, I have a pretty good full cycle. Tap 9, since it's 14 nanoseconds, 114, so it's really 14 nanoseconds, it is basically the same as tap 1. And then tap 10, since it's 126 nanoseconds, really sort of comes in, wants to come in and actually be here. And you can see that in the LEDs. So what you see here is you see basically the clock pulse. So here the clock pulse is coming in, and I use these delays to take a snapshot of it, and it's going to be lined up in one way or the other with respect to the PPS signal, which is what you're seeing. And you can see the fact that the 10th tap is in the wrong place when you see how when this will turn, when it wants to turn on, it's on, and when it turns off, that's going to turn off before that does, because again, it's really, in time wise, it's located there. And so tap 1's going to turn off, the light is going to turn off before the one for tap 2 as this edge moves through. But since tap 10 is further on, you're going to see that it's off, because again, it really belongs there in time for the clock cycle. So what I can do is, right now I'm running a little bit ahead, so there's a clock slip every 20 seconds, and I'm running fast. And so you can tell you're running fast because the edges, or this clock pulse, it's moving that way. And so that this is further back in time, which means that every second, the edge occurs earlier and earlier and earlier because it's running fast. And if I slow it down a little bit, just change the control word, you can see that the time it takes for an edge slip to occur will get larger, and that these edges are going to be walking. So now actually not are going to be walking over, and actually it's kind of starting to go the other way. Or maybe it's right there. No, okay, so it's ever so slightly walking back. And you can see how it's jittering, and that's the jitter in the PPS. And so now it's walking back the other way. And then I think when this gets updated, it's going to eventually go to a negative value. And what happens is, as you adjust it, as you get closer and closer to matching, the time it takes to slip an edge increases a lot. And then once you make it go to when it switches direction, it goes to a very, very long minus time. So that's what you're seeing here. So again, it's walking ever so slightly that way, and it's reflected by that. So if I slow it down by a lot, it should go negative. So now it's negative, and so I can adjust it. So what I want to do is, in the actual system, I can look for where this edge is. And so you notice I did 1 or 2 clicks back and forth doing this fine tuning. So I can look here, and if I notice that the edge has crossed over there, I can speed it up ever so slightly. And then when I see the edge walk back over the other way, I can, like it just did, I can slow it down. And so in this control loop, I can then have the edges just sort of go back and forth around one point very, very finely, rather than having to wait an entire second. And it's also faster. I can look at this and instantly know how it's running, and I'll instantly know how to adjust it. And this is basically what the oscilloscope is showing. So I have my oscilloscope here, and if you look, looks very similar. Here's the PPS signal, and I'm triggering off of that. And this is the 10 megahertz clock. And so the scale here is 20 nanoseconds per division. And so each one of the boxes is 20 billionths of a second. And each of these clock cycles, it takes up 5 boxes. So that's where you get the 100 nanoseconds. And right now I'm running plus 58 seconds per slip at least. So that means that I'm running a little bit faster. And you can tell I'm running a little bit faster because if you look at the edge, even though it's jittering, and that's the PPS jittering, it's walking ever so slightly to the left, which means, because I'm stuffing in, it's running fast, I get to stuff in more of these clock pulses every second. And I can actually show that by making it go a whole lot faster. So if you look now, you can see it's really marching. What you can also see is you can also see the jitter effect. And so even though it looks like it's standing still and it's jumping, what's actually happening is the PPS, it's jittering backwards kind of at the same rate that this wants to be marching that way, and then the PPS jitters back. That's why I get the big jump. And so if I were to make it be, if I just slow it down so it goes the other way, there you can see more of how that works. And so it marches and it jumps, marches, jumps, and that's the effect of the PPS jittering. And that jitter, it's about 15 nanoseconds. And I know it's the PPS jittering because when I have the 2 GPS clocks on there, I can see that the PPS edges jitter relative to each other, and I've had a stable reference running when the 10 megahertz is running, and those have no relative jitter to each other. So I didn't slow this down enough. But if I, and also the other thing I want to do is, there's an issue when the PPS occurs near the rising edge of the clock. That's where you get that, +1, -1 thing, which messes up my statistics. Knowing where that happens with the edges here, I can always make sure that I'm operating the system to avoid that problem where the jitter in the PPS causes me to think I've slipped a clock edge, only to regain it back the next time when it jitters the other way. And actually that occurs when there's 4 LEDs, when it's 4 LEDs on and 4 LEDs off. And so I need to actually measure that and look at it, and then that's when I know that I'm near the bad edge. So as this works its way over, I think it's when this edge is near that edge, because in the circuit here, I use the inverse of this to actually clock the circuit. So here's where I would have that problem, and that's when this edge is near that edge. And so if I wait till these two rising edges are aligned, that's when it's 4 off, 4 on. And so right where I'm here now, I avoid that counting issue with the jittering PPS clock. So I'm happy with how things are going. So this is the delay element right here. These are the two latches. Let's get rid of this. This is the delay element. Those are the two latches, and in the real implementation, I'm just gonna ignore these last two taps. This I/O expander is only 8 bits anyway, and so I'll maybe put it here, and I'll still have the light show. And then in the software, I'm going to make it so that there'll be some indication of where the edge occurs or what these LEDs are. So I might just have, an 8-bit word there that reflects the state of those LEDs. The other thing that's not apparent here is as I'm clocking it, I talked about the metastability before. There's a chance that wherever this edge is, I violate the setup and hold time. But I haven't really seen there be a jitter on that edge location, but I can filter that out in software. So it's good progress. So next time you see it, I'll have another one of the I/O expanders in there. I'll make the wiring neat, and I'll have some additional software display over there. All right, thanks for watching.